All right, this is section 5.3 AP Statistics. We have conditional probability and independence. I think I've only got 7 slides. This may go faster than some. All right, first thing is this, is that we have a formula that has some symbols that you may not recognize. And the first may be this bar, okay? And know that this means the probability of, and this means A given B. All right, so this symbol really means given. It's the bar. Okay. And what do we set that equal to? This is the probability of A and B all over P of B. Okay. Or you could write this the other way. You could say probability of B, again, remember that means given, A equals the probability of P of A and B all over P of A. All right, now, how do we use this in context? Well, here's what I have, and I'm gonna lower myself a little bit here. I have the same table that I've used in the past regarding Costco slices of pizza, all right? And so as I read this first question, and again, we're assuming that we're looking at people who bought a slice of pizza, what is the probability that a random person who bought a slice of pizza buys a slice of cheese, assuming, okay, I'm gonna underline that, it was purchased on a Sunday. Okay, so if we're assuming that it was purchased on a Sunday, the overall total doesn't really come into play a whole lot because I'm only concerned about people who bought on a Sunday. So let me look at the people who bought on a Sunday. Okay, so if I only care about people who bought something on a Sunday, then my total here is 600. Okay, now I'm going to show you the way that I think about it as I'm doing it right now. There's only 600, and then I'll show you the formula way. All right, and then on top of those 600 that were bought on a Sunday, how many people wanted a cheese? Well, it was this group right here, those 220. All right, and if you like, you can reduce. One quick way to reduce is if you do this, just take 220 divided by 600 in your calculator. And if I do that, I'll do this real quick. See what I get. 220 divided by 600 is your 0.3666 forever. Okay. And if I want to change this back to a fraction, just on your TI-84, all you have to do is hit math and then hit enter twice. Okay, and then I'll put it into its lowest form. Okay, so some of us do this in our head kind of quickly. That's really 22 over 60, which is 11 over 30. Okay, now that's the way I typically do these. I just like to look at the tables and the pieces within the table and answer my questions in this manner. If you want to use the formula, okay, and say that A is equal to someone who bought a cheese slice, I'll just abbreviate this, and let B be someone who bought a slice on a Sunday. All right, then what I have here is our formula, P of A given B is equal to P of A and B all over P of B. Okay, and so if I think of what P of B is, that's the probability of buying a slice on a Sunday. Well, there's 600 people who bought a slice on a Sunday out of 1,200. Okay, I'm not going to reduce, and I'll show you why in a second. And the probability of A and B, meaning you have to satisfy both a cheese slice and a Sunday slice. Well, your cheese slices are here, your Sunday slices are here, there are 200. Okay, so, sorry, not 200, 220. All right, and so you can see that the 1200s would each cancel out, and you're left with 220 over 600, and that's the same thing I have over here. So for me, I don't always do that because I just think it's easier to look at your table and look at the kind of the subtotal, which is now your new total, to help answer that question, and then pick the parts within your subgroup. In this case, it's the 220 to put it over the total of your subgroup. Okay? And I'll do the same thing here. I'm not going to use the formula. You can if you like. I just think it's easier not to because it's sometimes just conceptually easier to understand as you look at your respective table. So, all right, I'll do this one in purple. So it says, find the probability. Okay, again, we're assuming that someone bought a pizza, that a random person who bought a slice of pizza did so on a Saturday, assuming it was a pepperoni slice. Okay, so for all the people who bought a pepperoni slice, what's the probability someone bought it on a Saturday? Okay, so of all the people who bought a pepperoni slice, what is the probability that was done on a Saturday? And so, again, this word assuming is kind of like the word given. Okay, so there are 740 people who bought a pepperoni slice. And of all who bought a pepperoni slice on the weekend, Saturday there were 360. Okay, so that will go on top. Okay, and if you want to reduce it, you can. I know 10 goes into each of those, 36 and 74 times. And this reduces to 18 over 37. Okay. Again, you could do this the other way if you like. I said I wasn't going to do it, but let's let C equal a Saturday slice bought, and we'll say D is a pepperoni slice. Okay, and based off our formula over here, I'm circling now, or boxing. Okay, I'm only looking at people who bought a pepperoni, which is 740 out of 1200. Okay, and then in your numerator, you have to find the intersection of these two. Okay, so people who bought both a pepperoni and a slice on a Saturday, there's 360 over 1200, and again, the 1200s will cancel out and you get the same thing. Okay? All right, so that is conditional probability, which means, again, you're using this idea that there is a subgroup that you're really collecting information on, not over the total group. All right. I'll have to keep moving my screen around, but this is called the general multiplication rule. And you notice that it's actually a form of the previous equation. So if you look at, let's see, P of A intersect B all over P of B, and we'll set that to, that was really P of A given B. Okay, if you just kind of cross multiply, you put a 1 there, but cross multiply, that's P of A given B times P of B is equal to P of A intersect B. All right, and this is one variation of that formula. If you had these A's and B's in reversed, and you had an A on the bottom here, which is the other way of writing this formula from the previous screen, then when you would get this over here, okay, the one that's underneath. All right, and the only difference is they reverse these two items. Okay, so Raising Cane's Chicken Fingers, one of my favorite places. It says it is found that 60% of teenagers eat at Raising Cane's at least once per month. Okay, and found that 80% of all teenagers who eat at Raising Cane's Chicken Fingers once a month substitute their coleslaw for another slice of bread, which you are allowed to do, okay, for free. It says, what is the probability of randomly selecting a teen who eats Raising Cane's Chicken Fingers at least once per month and substitute his or her coleslaw for garlic bread? All right, very wordy question that has a very simple answer, okay, or process for an answer. Let's let A be teenager who eats at Cane's okay, once a month. Okay, let's let B is a teen who eats at Cane's once a month. And substitutes. I'm going to say sub if you don't mind. Bread or slaw. Okay. So what I had is they want to know what is the probability that both of these happen. Okay, that you actually have a teen that may eat there once a month, and further that teen also eats an additional slice of bread versus the coleslaw. So your P of A and B, if you don't mind, is equal to P of A. Let me fix that, sorry. Okay, P of A times P of B given A. All right, so A is a teen who eats at Cane's once per month, and that's 60%. That's already given right here. Okay. P of B given A. Now, we have to assume that this teen already eats at Cane's once per month, and that if that's the case, that they substitute their bread, and that's going to be, sorry, their slaw for the bread, 0.80, and you just got to multiply them together, 0.48, okay? And you are done. Okay, emphasize this word here, and. Okay, look for that. That's usually in the question, and that kind of helps us move through this problem a little bit more easily. Okay. All right, and I'm going to do this just because it bothers me. This eats doesn't look clean. So I'm just going to fix that real quick. All right, it's probably the most awkward question to read. However, if you can pick it out, all right, and then understand what part is A and what part is B, that makes it pretty easy. Okay, the math for it's really simple. All right. Fabulous basketball player, not a pro basketball player, but great shooter, friend of mine. Brian Special makes makes his first of 2 free throws in basketball is 94%. Okay. If he makes the first free throw, which means he usually gets a second one, okay, the probability he makes the second one is 98%. Right. If he misses the first free throw out of 2, then the probability that he makes a second free throw is 88%. Okay, so we're under the assumption that we know the rules for basketball, and if someone is fouled and has to shoot free throws, there's typically 2 that are shot. Okay, there's the first shot. I'm going to put this on the bottom, and then there's the second shot. Okay, now the probability of making his first is 94%. So you're going to make the first shot, or you're going to miss the first shot. Okay, the probability of a make is 0.94. The only alternative of making a shot would be to miss a shot. You can't do anything else. So to find the probability of a miss, you're just going to take this and subtract it from 1. That'll give you 0.06. All right, now from there's a second shot. It says if he makes his first free throw, the probability that he makes his second free throw is 0.98. So we're going to call this a make. Probability that he makes the first is 0.94. If that's the case, the probability that he makes the second is 0.98, which means the probability that he would miss is 0.02. Okay. Further, he could miss the first one, but make the second one. And that happens sometimes. If he misses the first, as you see this right here, the probability that he makes the second is not as high. It's only 0.88. And again, the probability that he misses is 1 minus this, which is 0.12. Okay. All right. Now, before we move further, here's what I want you to do. We've set this up very well. I want you to take a moment. I'm going to have you pause this. All right. And I'm going to have you do some calculations. Okay. What I'm going to have you do is you're going to have you multiply through this tree diagram just like we typically would. So for example, multiplying by 0.94 by 0.98 would be the probability of actually making both free throws. Okay. Multiplying the 0.94 times the 0.02 is the probability that he would make the first and miss the second. Okay, so what happens with the second free throw is kind of determined a little bit by what happens in the first. Okay, and that's why we have these different percentages. So if you don't mind, take a moment, pause this, okay, and then I want you to make those calculations to those 4 possible outcomes, okay, and then we'll see if we have the same thing, okay? Okay, so here are the 4 probabilities that I've got for the respective makes and misses and free throws. And remember, you can make them both. You can make the first and miss the second. You can miss the first and make the second, or you can miss them both. And here are the 4 that I got. Okay, since those are the only 4 outcomes, you can check to see if your work is right by adding them up. If they do equal 1, then that is a good sign. Okay. All right, so the question for part A says, what is the probability that he makes both free throws? Okay, and so you found that probability. You multiplied both of these numbers together, and we got 0.9212. What is the probability that he makes 1 free throw? Well, be careful with this, because remember, he can make it and make the second. He can make the first and miss the second. You can miss the first and make the second, or you can miss them both. Okay, so those are your 4 outcomes. If I want to find the probability that he makes only 1 free throw, that actually means these 2 items, they both have 1 make only. All right, so what I need to do is include 0.0188 and 0.0528, and we're going to add those together. Okay, so 0.0188 plus 0.0528 gives you 0.0716. Okay, so make sure you do have both of those. Okay. All right, finally it says, I say both of those that we're adding together, because both are representations of 1 free throw. All right, last thing it says, assume he makes only 1 free throws. What is the probability that he makes the second free throw? Okay, so this part right here is kind of like my given. Okay, so let's let event A and event B be something. I'm going to start with B, and I'm going to use the formula just to organize my thoughts a little bit. Okay, B is that he only makes 1 free throw. Okay, and I'm going to abbreviate free throw if you don't mind, FT. And A is that he makes the second. Okay, so if I consider my formula, P of A given B, okay, and again, the given part is the only makes 1, equal to P of A and B all over P of B. Okay, so what is P of B only makes 1 free throw? Well, we've actually answered that. Okay, the representation for only making 1 free throw is right here in B. I'm going to circle it. You've actually found that. That's 0.0716. Okay, and then what you have to ask yourself is, amongst those items that gave you exactly 1 free throw, which one represents the second free throw? Okay, because I don't want just this part right here representing second free throws, which is this guy and this guy. Those are both mixed for second free throws. But which one of these 2 represents making the second free throw? Okay, and it looks like it's this one here. Okay, which gives me this result at the end, which is 0.0528. Okay. So, by the way, this wasn't used before. It was actually this one. Okay. It's this group here and this group here that represented one free throw being made. And this is the group that's one free throw being made, but it's the second free throw. Okay. So we're looking at both of these together, okay, to represent this group. Represent the bottom group, but then the item on top is going to be the one that's more specific, okay, the one that says the miss and then the make, which is what they're asking for. All right, little key here, make sure you put your plus sign when you're using this. Put your plus sign here too if you're somehow trying to show that you are adding these together. Don't do that. They could mark you off, as they have in the past on AP exams. Okay, so if we divide this out, 0.0528 divided by 0.0716, I get 0.7374. Okay. All right, giant conditional probability problem. Kind of a form of Bayes' theorem, if you know of that. Okay. All right, let's move on to question 4. Look for this. They usually have these problems with, by the way, I will say illnesses, medications, and testing for cancer or HIV, etc. So if you see something that deals with testing for illnesses, this relates to it. All right, testing for independence, right? Again, this is probably the last time we'll use this Costco problem because I know you're sick of it. I'm a little sick of it, even though I love their food. So we're going to do a test for independence, and I'll show you 2 ways to do it, okay? Here's the first way, and we'll just see if cheese and ordering on a Sunday, ordering a slice of cheese or ordering on a Sunday are independent from each other, okay? And here's how we'll do it. Let's see, where's this? P of A given B. So the probability of, I'll just say this, A is getting a cheese, given that you ordered on a Sunday. Okay, and so I'm just using this piece right now. If you look at the Sundays, there's 600. Okay, if you look at the A, which is part of that 600, okay, we got 220. Okay, and then what I want to do is, since I've answered this, I want to see if that's the same as P of A. Okay, and if you just look at the plain P of A, that's just the probability of getting a cheese. So how many cheese do I got? I got 460 all over 1200. And I'm just asking, are these the same, yes or no? And if you divide them out, they are not. Okay, so we'll say that cheese pizzas, okay, and ordering on a Sunday, okay, are not independent. All right. Another way to do it, okay, is by using this formula for a test, and I'll do this part in blue. P of A and B. So this is a second test. Depends on which information they give you to help you decide which formula you'll use, but sometimes there's enough where you can do it either way. But P of A and B. Okay, this is going to be out of 1200. I'm going to do this part right here. A and B means it has to be cheese and on a Sunday. Cheese and on a Sunday, there's 220. So there's cheese and Sunday, 220. And what I want to do is see if that is equal to what I would have here, this P of A times P of B. Okay, probability of just being a cheese is again 460 over 1200. Okay, and if you multiply that times P of B, which is just being a Sunday, okay, Sunday is because that's what this is B. This over 1200. Okay, what you'll find is you'll get 220 from the original over 1200. Okay, this part right here, okay, is equal to 230 over 1200. And those are not the same. So another way to show that they are not independent. Okay, so if they ever say, you know, are these items independent, yes or no? They want math, okay? They don't want some type of verbal explanation to justify your work. So use one of these two formulas, okay? If they ever say this is independent or ask if they're independent, notice I have them in big caps there so that it's very easily visible to you, and you'll have to look for that on your homework, okay? Okay, here's my last question. It says the probability that this soccer player, Christine, who is a superstar, earns a yellow card during any soccer game for violently slide kicking and tackling an opponent to the ground is 0.62. Okay, maybe she's just a real aggressive player. A 4-game tournament begins this weekend, and as an incentive to stay in the game, the coach offers Christine a milkshake if she can go through the entire tournament without getting a yellow card. Okay. Now, assuming that one game has no influence on the next, what is the probability that she can go 4 games without a yellow card? Okay, so let's let A be equal to getting a yellow card. Okay, and she's playing in 4 games. So what I want is I'm going to want that A is equal to 0. Okay. Let's do this. Instead of getting a yellow card, how about the number? Getting a yellow card. Number of yellow cards. I'm going to adjust this real quick. Number of yellow cards. Okay, and I want 0. There, that's better. Okay, so I've got 4 games. Okay, I've got game 1. I've got game 2. I've got game 3. And I've got game 4. Okay, well, the probability of getting a yellow card, okay, is equal to 0.62. And so if I want the complement of that, okay, that's going to be 1 minus 0.62 or 0.38. Okay, so the probability that she gets no yellow cards on the first game is 0.38. Probability she gets none on the second is 0.38, and the third, and the fourth. Okay, and what are we going to do with these here? We're going to multiply them together. Okay, so again, that's the probability of not getting a yellow card, means that she has 0 yellow cards in her game. Okay, so 0.38, we're going to multiply that by itself. And I think she gets this. I think she gets 0.02085. Okay, let me check my work one more time. Okay, and I got the same thing. Okay, now here's the last thing. It says, what is the probability of earning a yellow card in at least 1 game? In at least 1 game. So the probability that A is 1 or more. Okay, now here's the challenge. I'm going to kind of do this off to the side here. These are the number of yellow cards that she can get. Okay, the fewest that she could get is 0. Okay, but the most that she could get is, well, she plays in 4 games. Okay, we'll assume that there are 4. All right, now here's what they want. And remember that there are no other options. They want the sum of these 4 probabilities. Okay, and by doing all 4 of those, that would be kind of a challenge. Okay, it's a lot of different mathematics in order to get each of those results, and then you'd have to add them up. okay? But here's what I know, is that while these 4 would answer the question, okay, these 5 together must add up to 100%, because those are the only 5 outcomes that could exist in terms of the number of yellow cards that she could get. Okay, so here's what I can do, kind of a secret. The probability of getting at least 1 is the same as 1 minus the probability. Oops, I wrote that off. Sorry, almost done. 1 minus the probability of getting, well, the complement of this. The complement of the probability of 1 or more is less than 1, which is 0. Okay, so the probability of A being equal to 0. So basically, you're doing one of 2 things. You're either getting none, which is what we want. You're going to get a milkshake if you get none, or the alternative, which means you'll get at least 1. Okay, and again, they want to know this. And since, again, all 5 of these together must add up to 100%, and I want these 4 collectively, as long as I know this guy, all I have to do is subtract that from 1, and I'll have the answer to the collective amount for the other 4. If that makes sense. And what's cool is, in part A, right here, I'm going to circle this really big, you found that answer. Okay, and what does that give me? Well, it gives me 0.971. So how about, yeah, 0.97, how about this, 915. Okay, and that is your answer. And it is a super quick way to answering a problem that's actually very large. Okay, so if they ever give you something that says 1 or more, that's a trap. Okay, what you want to look at is 1 minus the probability of whatever they're asking for. I'll just say A is equal to 0. Okay, so, and the 0, 1 is easy to do. And then once you get that, you can subtract that from 1, that answer from 1, that probability from 1, and it'll give you everything above that, everything above 0. Okay. All right, here's your homework. I'm blocking myself out. Some of you will use that as an excuse not to do this. Okay, there you go. If you have any questions, you let me know. Have a good day.